All right, so the next talk of this session will be given by Eoin O'Connor, and he's going to tell us about bounding fidelity in feedback control protocols for quantum state engineering.
Thank you. Yeah, so, sorry. Yeah, my name's Eoin, and I'm a postdoc in Milan with Marco Giannoni. And so the problem I'm looking at today, so in general, if you're trying to derive some kind of optimal control strategy in the presence of, with feedback control in a continuously monitored system, this is a very hard problem to find what the optimal strategy is. It's hard to compute, difficult to compute, and it scales very poorly as you increase the system size. And so if we could find a way to put a bound on how well you could do without having to do this difficult numerical simulation, then that would help us to choose which kind of problems are even worth trying to solve, and it would help us to understand when we've already gotten close to what the optimal solution is. And so we're going to consider this setup that I'm sure you've seen a lot already, where we have some control Hamiltonian, we have some environment that's causing dissipation, and we're continuously monitoring the system, so we have this stochastic measurement term here. In general, we're going to consider kind of best case scenarios, so we're going to allow for state-based feedback. So based on our measurement record, we're going to update the state in real time, and then we can choose our control strategy based on that updated state. And the quantity that we're going to try to optimize is this kind of trajectory average fidelity, where our fidelity is taken with respect to some pure target state. So we're trying to prepare a target state and stabilize the state around that target state. And when you have this dissipative dynamics, generally it's not always possible to deterministically get all of your trajectories to that state at the same time. So we're trying to put a bound on how well you can do that, how close you can get on average. So this is a hard problem to put a bound on because you're able to choose so many different possible control strategies. And when you perform this average, it's impossible to do it without making some assumptions. So the way we do this is we assume everything, all the stars are aligning. We have the best case is always happening for us. And so that involves assuming unit efficiency detection in our measurements. And we're going to assume then also an initial pure state of the system. And then the way we're going to bound it is we're going to take each part of this master equation and bound how that changes the fidelity individually. So we're just going to define some terms. We have first the unitary part. This is how the Hamiltonian changes the fidelity. This is how the Lindbladian part changes the fidelity. And this is how the kind of measurement back action will change the fidelity. And we're going to try to put a limit on average on how large these terms, how large each term can be. Okay, the measurement term is easy because when we average it, the Wiener increment is independent, and so we just get 0. So that's the first term done. Moving on to the Hamiltonian term, we can just apply Cauchy-Schwarz inequality, and some of you may be familiar with this derivation. It is exactly the one used to derive the quantum speed limit by Mandelstam and Tam. And in general, with this problem, we have to put some kind of limit on how large the Hamiltonian is. If we allowed for an arbitrarily strong Hamiltonian, then we could prepare a state with whatever fidelity we want. So we need some kind of constraint on what the Hamiltonian is, and we're going to choose to bound this term here. So the variance of the Hamiltonian with respect to the target state. And we're just going to say it's less than or equal to some number that we choose as an upper bound at the start of our problem. And so this trick allows us to take out this variance term when we do the averaging. And then we just need to average over the conditional fidelity. And we can do that by just applying Jensen's inequality or Cauchy-Schwarz, whichever you prefer here. Okay, so now we've bounded the first two terms as a function of the rate of change of the average fidelity as a function of the current average fidelity. Finally, we need to take into account the Lindbladian term. And to do this, we're going to assume, we're always in the optimal orthogonal state. So we can take our conditional state here, split it up into the part that's in the target state and the part that is in some orthogonal state. And this is generally going to be conditional on the dynamics. The phase is conditional. Everything is conditional here, but we can always split our state up like this. And simply subbing this into the rate of change of fidelity due to the Lindbladian and optimizing over the phase, we get this term here. So we get 3 different contributions to the rate of change. So we can interpret this delta C squared term as just the flow rate, how fast the environment is taking us out of our target state, given that we already have some fidelity in it. This A term is the flow into the target state due to the environment. So given that how the environment is taking us from the orthogonal state into our target state, so it's helping us. And this B term is a kind of a more complicated interference term that I'm not going to dig into now, but luckily it's 0 in all of the examples we're going to look at. And so, okay, one more step is we have to do this optimization. So here we still have conditional terms in A and B. And so we have to optimize A. We have to choose the orthogonal state which maximizes A and B. And we're going to do that individually. And when we do that, now we've bounded all 3 terms, and we can derive an upper bound on the rate of change of the average fidelity with respect to time in terms of these. So these are the optimized values of A and B. And so essentially, this is kind of like deriving a quantum speed limit on the rate of change of the average fidelity. There are a number of things we can do with this rate equation, but one thing is you can solve for this kind of steady state limit. You can look for when you find this balance between the trade-off from the environment and the driving and the other terms. And you can write down an equation for the steady state fidelity is always bounded below, or is always going to be less than this BQ term, which is a kind of complicated term and difficult to interpret. But the point is we've bounded the average steady state fidelity of any possible optimal control strategy in terms of quantities that only depend on your jump operators and the strength of your control Hamiltonian. So that represents one of our main results. Another main result is previously in 2019, Kobayashi and Yamamoto derived a bound under exactly the same assumptions that we use. And we were able to prove that our bound is strictly tighter than their bound. And it becomes easier to interpret if you have the case where A and B are both 0. Now you can see the bound, there's a clear trade-off between the strength of your Hamiltonian and the rate at which the environment is taking you out of the target state. And you can see that as long as your target state is not a steady state of the Lindbladian dynamics, it's impossible to prepare kind of with unit fidelity deterministically on average your target state. And this term, as I say, is independent of the orthogonal state, and so that means it's going to be more accurate in general. We're going to consider a specific example now. So we're going to look at n non-interacting spins in the presence of a collective dephasing here with a dephasing rate kappa and a collective damping term with the rate gamma here. And so this gamma is going to be taking it out of our target states, which are going to be the Dicke states. The Dicke states are the common eigenstates of the collective angular momentum operator and the Jz operator here. And our control Hamiltonian, we're going to allow for kind of a linear combination between Jx and Jy. And we look at 2 scenarios, one where you can use your feedback control to control both the strength and the relative phase between Jx and Jy, and one where we just choose a fixed phase and only control the strength. Our limit on the variance converts into a limit on the absolute value of this strength term U of t in front of the Hamiltonian. So subbing this into our original formula that we saw before, in this case, A and B are 0. A is 0 because for a qubit, n equals 1, and trying to prepare the excited state, there is no state above the excited state that can kind of decay into the excited state. And so we get this nice bound here, where we see a clear trade-off between the strength of the damping and the control strength of the Hamiltonian. Okay, so that's nice to have a bound, but how well does it do in practice? So the blue curve here is our bound. Orange is the Kobayashi bound. That was the previous best bound. And we see here is the found optimal control strategies for controlling this system in the steady state. And we see that we actually get very close to what you can achieve. And there's always going to be a bit of a difference, and this difference here comes essentially from this Jensen gap. So you have to apply the Jensen inequality because we have this distribution over conditional fidelities. And so you're always going to get this gap, but this is as close as you can get. The only inequality here is this Jensen's inequality. And we see that having control, being able to optimize over the phase is very useful, especially for small values of gamma here. We can sub these bounds into the general Dickey state preparation problem. And so when we're trying to prepare the maximally excited state, this is when all the spins are spin up. We just get this additional factor of n in front. Again, this is because there is no state above the maximally excited state that can decay into it. So we get this nice bound. For preparing the highly entangled Dickey state, it becomes a little more complicated. And we get this factor of half because we're kind of assuming that all of our, we're in the orthogonal state, m equals to 1, and we're always decaying into our target state, which is somewhat unrealistic. One thing you'll notice immediately is that in the large n limit, this says the system is completely uncontrollable. And so if we want an actual interesting problem, we're going to have to assume that this coupling strength for the collective damping is going to scale inversely with n. And in practice, this is really how it shows up. Okay, so subbing in our bounds again, looking at the n scaling now for a fixed gamma. And we see that we get a little bit of a bigger gap between our bound and the phase control, but still it captures the general idea of the problem. It tells us that, yes, you can control it in the large n limit, and we find that this is the case. Now, it's really, really important that we can control both the strength and the phase, because we have so many different relative phases showing up. If the fixed control just struggles to align them in any kind of coherent way. Then for preparing the zero state, the bound is essentially useless. It tells you, oh yes, it's trivial to prepare the zero state. First put your state in the m equals 1 state and then decay into it. But in practice, that's not possible. And so, yeah, I guess nobody's surprised. It's quite difficult to prepare the Dickey zero state. And so if we want to come up with a more reasonable bound for this state, we're going to have to make more stricter assumptions, because we're allowing for a very large class of Hamiltonians that are only restricted in terms of their variance. So now we're going to apply much stricter constraints on the actual problem. So we're going to specify we've got homodyne detection on the collective dephasing, heterodyne detection on the collective damping term, and we're going to allow only this kind of control Hamiltonian. And so with these assumptions, we first notice something interesting, and that's that the transfers only occur between neighboring values of the angular momentum. So this means if we decompose our conditional state into the Dickey state basis with the population and a phase, we can write the rate of change as the population as a transfer rate from m plus 1 into m minus the transfer rate from out of m into m minus 1, plus some stochastic part, which we're going to ignore for now. This transfer rate, we can write it down. It's quite simple. So we have the rate. So depending on the population of m plus 1, you're damping. So this is the damping term. And then you have the Hamiltonian control term. 2 minutes. Okay. That depends on the phase of the control Hamiltonian and the relative phase of our state. And then these HM terms are essentially the J plus factors. And so we can see immediately why we need this inverse scaling in gamma, because HM squared scales like n squared here. So we need a 1/n scaling. The best case is when all of our states are moving. We have our phases aligned such that all the states drive towards the target state when we turn on our Hamiltonian. And under these assumptions, we can look at the steady state again, and I'm going to skip all of the details, but it's a similar kind of derivation to earlier, and we can write down a new bound for the steady state of our target state, the steady state fidelity of our target state. And one thing we notice here is that unless we're preparing the ground state, all of these terms actually become infinite in the large n limit, and so again, we do need this inverse scaling with gamma. And yeah, again, it's independent of the coupling constant kappa. Okay, on one final plot, we see this new bound. It does slightly better for the excited state. And okay, I'll leave the green line for now. I haven't introduced it, but what's important is for the Dickey state, we get a much better estimate of how well you can do in practice compared to the original bound. Okay, and I'll just leave the conclusions, and thank you very much for your attention.
Let's thank Eoin for this nice talk. Are there any questions? I have a quick question. So when you sort of put the dephasing and the jump operators in your Lindblad, they were all collective.
Yep.
Can you speculate if they sort of act locally on each of the qubits? Does all of this go through?
So you can write down the bound. Mm-hmm. In general, the problem is, imagine you have like a local dephasing. So in the Dickey states, this doesn't generally even conserve the collective angular momentum. And as soon as you leave your collective angular momentum space, you can't use the coherent control to get to the target state. And so you have to wait until it fully decays all the way to the ground state and then again. Mm-hmm. So you can write down the bound, but I suspect it will be very inaccurate.
I see. Okay. Okay. Are there any further questions? Any questions from the online audience? Okay. If not, let's thank Eoin again for this talk.